Welcome to the lecture on coordinate systems, positioning ourselves on the surface of the Earth. Not actually collecting GPS data or anything like that, but just the numerical part of this. Where are we on the Earth according to a particular coordinate system? And how is that? How do we know this? How do we define a coordinate system? How do we know where here is? We've seen this slide before, the spatial data. We want to know where something is, and we can describe it as being in a particular position, but that only actually is in relation to something else, everything else, other things. We have no absolute position, either in the universe, on the surface of the Earth. It is always in reference to some other thing, feature, point of reference. It's a reference system. We are such a distance or such an angle from something else. That is the best that we can get. So if we now know that no position is absolute, there is no coordinate system pervading the entire universe, that independent of what we think, independent of the position of the Earth in space or anything like that, we then have to have a definition of a coordinate system that can take care of this insecurity, that allows us to position ourselves and gives us the necessary information to be reasonably certain, reasonably being adequate for our needs, of where we are. So we are describing this relationship to some other place, and how we describe that will vary depending on what we want to do, depending on what the reason for creating this coordinate system is, what our intended purposes are. Some of these will be global references. We'll have a system that places us in reference to a starting point on the Earth, and the reference system will cover the entire globe. And others will be local. Some of the local systems are connected to the global systems, others are completely free and independent of the global systems. All reference systems are wrong. They are all simplifications in some way. They cannot fully represent the entire surface of the Earth accurately. Just in the same way that a map is always wrong to some degree, coordinate systems contain errors. It's unavoidable. But we can hope they only contain small errors, that we have a good reference system in which the errors are small, but that only means in relation to what we want to do with that coordinate system. So a coordinate system may be adequate for one purpose, inadequate for another, or inappropriate for another purpose. So these things are products very much for an intended use, as well as being derived from something unavoidable as the Earth. If we look at local reference systems, they exist on a sliding scale. As I've mentioned previously, we have coordinate systems that are entirely local. They don't care about the rest of the Earth. They just sit there in reference to some local feature, such as a house or a city. And then others that are connected to everything else, say within a country or even on the entire Earth. They're still locally relevant. Their applicability is limited to a particular area, but we can take that coordinate system and connect it to everything else in the world mathematically with a reasonably simple set of equations that take our position in this local coordinate system and can very rapidly reference us to any other point on the surface of the Earth. These local reference systems almost always are intended to describe a flat surface with linear distances, something that we sort of think of as experiencing every day. The world is flat. We think of it like that in our everyday experience, even though it actually isn't. I really, really hope that is not still a debate. The world is not flat, so we have to make a flat surface for convenience, for our everyday use. And normally what we will have is an X and a Y axis that are orthogonally opposed. There's a right angle between them, and distances along them are linear in this local reference system. Linear as in 1 meter, 2 meters, 3 meters, 4 meters. We can just carry on along that line and it'll increase at the same rate along that line. So our local reference systems might look something like this, where on the left we have a very local system, completely disconnected from the world. It's applicable only to this very small area. And in the silly example that we have here, our axes for X and Y have been defined as the walls on this house. Now, the surveyors among you will hopefully right now be crying out, going, no, don't do that, because this is not actually a very good way of defining a system. These walls may not be entirely square. There might be a small error in them, and that error will increase with distance from our starting points. So this is actually not a very good way of defining our coordinate system, but for the sake of illustration, it will do for now. So we have this locally defined system. We don't know where on the Earth we are, but we don't need to, because this is only for working in this small area. We want the relationships between these houses here. On the right here, we have a coordinate system that is national. The coordinate system covering an entire country. And we've defined the starting point as being 15 degrees east of something else on the Earth, which is Greenwich. But still there's this connection. We have a 0 point somewhere where we can start counting from, and then we do our counting from there. And this covers the entire country, but is related to the globe as a whole, to the Earth as a whole. Still a local system, really only for use in this area. Once we move outside of this area, the coordinates become, we get errors in the scales, which means that it becomes not very useful. Locally applied, fine. Moving away from this area, not fine. Then we have our global reference systems. These tend to work in a slightly different way. The geodetic systems that are used to reference everything on the surface of the Earth, generally speaking, will be using angles rather than linear distances. They will be using angles of longitude and latitude, plus maybe a height as well. So we find our position on the Earth, we define it as being a particular angular distance from our starting point. And we have the equator, which is a natural kind of line defined around the Earth. We have the Earth rotating around this way, and the bulge out, this maximum bulge as it were, is the equator. The Earth is rotating around this way, so that gives us this line quite neatly. This other line though, how do we define that? We just draw a line. This is how we've defined our longitude here. We've defined it as starting at some point. The equator was easy enough because there seems to be this natural boundary here where as the Earth is rotating around, we can define this line here as being the boundary between this upper half and the lower half. But because we're rotating around this axis, there is no natural boundary along here, and we just define a line. And it's defined in almost all cases as going through Greenwich in London. This is for historical reasons. When this became a point of, for a long time was a point of issue, but when ultimately a solution could be found, how to solve this, it just so happened that one of the strongest empires on the globe at the time was the British Empire, with its capital in London, and so because they had the biggest boots, they got to decide where it was. Nowadays, that might fall somewhere else. Somebody else will be able to make the decision. One would hope that perhaps it would be more collaborative. There was some collaboration in this, to a small degree, but generally speaking now it's defined as going through London, and there's not really much point in changing it, except if you wish to, for cultural reasons, redress a balance. But mathematically it makes no odds. It really does not matter. We have to start counting somewhere, and we've just taken Greenwich as our starting point. And this coordinate system, as I said, defines everything in terms of angles. It's not a distance that you can walk along. It would change. We can illustrate this quite, hopefully you can see that this angle here, the longitude, as we move up closer and closer to the pole here, the same angle will cover a smaller and smaller part of the surface. So it's not very easy to work with. You know, it becomes quite difficult if we want a nice flat surface to be using angles, because it just changes all the time. It's easy, it's a relatively straightforward calculation, but it's not convenient for our brains to think in those terms. So we'll need to do something about that later on. But for defining a point on a globe or on an ellipsoid or something like that, great, these angles are very useful. It's a better way of doing it. There is another alternative using x, y, and z with linear coordinates, where we start off in the center of the globe, this geocentric Cartesian system. The problem is that we don't live inside the globe. We live on the surface of this, and moving around on this surface, every step we will make in one direction or another, doesn't matter where we go, will involve a change in all three coordinates, which is kind of inconvenient. It becomes very difficult to just hold one axis constant and move along another one. So we don't use this, generally speaking, for life on the surface. This is restricted to existence within the globe. What does that mean? Well, actually, we only use it for something called datum transformations, generally speaking. There are a couple of other uses as well, but quite often it's for these datum transformations. Gravimetry also can use these as well. It's a side point. But so this is something that be aware of. You're probably not going to encounter it until you actually have to do something called a transformation between different coordinate systems, and then this might come up, but the computer will deal with that for you. But this is what's going to happen.